Okay, good morning. So it seems there's a bit of confusion regarding my... Seriously? All right, let's review then. Let's review. All right, let me reassure you. So if that's a general consensus, the grading will be, I'll take that in consideration when the grading comes, okay? But the most important part about Thevenin and Norton is basically the setup of the problem, okay? The analysis is not new. It's not a new analysis technique, say. So you learned about Ohm's law, KVL, KCL, node voltage, mesh current. All of those are analysis techniques, right? Thevenin and Norton are not analysis techniques. Well, I mean, in the larger sense, yes, they are analysis techniques, but I hope you get what I mean. The most important part about Thevenin and Norton is to set up the problem correctly, set up the circuit correctly. After that, it's still Ohm's law, KVL, KCL, node voltage, mesh current, superposition, or any analysis technique that you wish to use. The reason I stress a lot of importance on Thevenin Norton is, well, it's very important in the field of electrical engineering, but specifically for this course, when you deal with circuit design and circuit analysis using diodes, transistors, you should be able to perform a quick, like when I say quick, like within a few seconds or a few minutes of setting up your diode or transistor circuits. For example, there might be 3 or 4 resistors in front of a transistor, and you'd have to find the equivalent Thevenin resistance as seen by the transistor. Okay. So let's go to the notebook. And so I brought this up. And let's see, make sure sharing the notebook. All right. So this is page 20, slide 20 in our class notebook. So we have this circuit. We don't really care what the circuit is or what it does, but we have this resistor at the far end, right? R6. So if you're trying to find the Thevenin or the Norton equivalent circuit as seen by that resistor, those words as seen by means that that is to be considered as the load. And the load is never part of the Thevenin or Norton analysis. So you remove that, which is what I was showing here. So you remove R6 from your analysis. That leaves behind the rest of the circuit. And also, you now have 2 open terminals where the component was connected. So those are your terminals of analysis, just right here. And so from that point on, you set up the circuit to determine voltage, resistance, and the current. The voltage doesn't need any setup because once the component is removed, you have 2 open terminals. You simply measure or calculate, in this case, calculate the voltage at those terminals. That is the circuit that is required. So when I was saying don't overthink this, that's what I was trying to say. Does that make sense now, hopefully? And then when we want to find Norton current between those same analysis terminals, all we do is we place a wire between those terminals. For Thevenin resistance, however, we need to remove or reduce all the sources to 0. And reducing a source to 0 means replacing a voltage source with a short circuit and a current source with an open circuit. So Thevenin resistance is the one that actually requires the most modifications in any circuit. But voltage and current, Thevenin voltage and Norton current do not require much modifications. Once you figure out or once you determine the load for the circuit, you remove the load and then you analyze the rest of the circuit without the load. Yes. You can use Ohm's law to do that, but if you recall the examples that I showed in class and hopefully also did the homework, it's not always possible to determine Thevenin resistance. So let me back up. So the question being asked is, once we have 2 of the 3 quantities, can we use Ohm's law to determine the third? The answer is yes, you can. However, if you have only 3 quantities and you use 2 quantities to find the third, you have to be 100% confident that your answers are correct. Because if even one of those two is incorrect, then your third quantity is also going to be incorrect. That's one reason. The second reason is if you have dependent sources like this one in your circuit, we cannot reduce them to zero, so we cannot find resistance that way. So we must find a Norton current first in order to find the Thevenin resistance. Does that make sense to everyone? Right? So engineers do need to know how to find all three quantities. And specifically for transistor models, that's actually where this model comes from, bit I1. Transistor model will have dependent current sources, and so it's not possible to find Thevenin resistance directly. We have to find, or we must find Thevenin voltage, we must find Norton current, and then we find Thevenin resistance. But again, let's back up. So in the quiz, I had 3 components listed. Each one of those components, meaning find the Thevenin, Norton, and Thevenin resistance as seen by that component. You remove that component from analysis, meaning that's the load. It doesn't matter that it's the voltage source. You remove it from the circuit. It leaves behind 2 open terminals. Those terminals are where you would analyze for Thevenin voltage, for Norton current, and Thevenin resistance. So 3 circuit diagrams for 1 voltage source. Then you have 3 circuit diagrams for the current source, and then you have 3 circuit diagrams for, I don't know what this was, one of the resistors, I believe. So 9 circuit diagrams in all. But it's essentially the same circuit, except the load is different for each one of those. That's what I was asking. Yes. That is correct. So the question being asked was, the sources are kept for the Norton current and Thevenin voltage, and the answer is yes. For Thevenin voltage, if we want a voltage or current at the output, then we must have some sort of energy source in the circuit. So there is no other modification to be made. Thevenin voltage, as I said, it's like there is no setup, there's no modification to be made for the setup. Once we have identified the terminals of analysis, that's it. Nothing else needs to be changed. Terminals of analysis. That's why, if you recall, I stated in the lab or in real life, if you're working with a circuit, if you wish to determine Thevenin voltage, there's nothing to be done. You simply take a multimeter, measure the voltage at those terminals. That's your Thevenin voltage. So I believe you might have done that in 113, perhaps, measurement of the voltage. That's 2 years ago, 1 year ago. 113, when do you take 113? Circuit analysis. Circuit analysis 1. Okay, so, but anyway, so Thevenin voltage measurement, all 3 quantities to measure in the lab takes literally less than 2 minutes, not even 2 minutes. Your circuit's done correctly. You have your 2 measurement terminals. You take your multimeter, you connect it at the output terminals right here. Oh, not plus minus. It's a meter. So you connect it here, put it in voltage mode, measures the voltage. You don't do anything. You simply change the mode and the physical terminal on the meter, change it to current. A multimeter in ammeter current measurement mode is a short circuit. So you don't need to short the circuit. Remember, we need a short circuit. If we have a meter in current measurement mode, it's going to provide the short circuit as well as measure the current itself. Now, that's why I said actual real life measurement does not take more than 2 minutes. All right. Questions? What other questions do you have? It's fine. It's fine to ask questions. I keep stressing on this because again, it's an important topic. As an EE, if there's one thing that you should remember, well, actually it's 4 things: Ohm's law, KCL, KVL, and Thevenin Norton. Yes. Yeah, that's for measuring. If that's if you have a dependent source in there. So the question being asked is if you have, the way you remember doing this is you connect a voltage source at the output terminals and you find the current flowing supplied by that voltage source, apply Ohm's law, and you determine the resistance, which is fine. You can do that too. You can do that too. But again, it requires analysis, right? Okay. The easier way is to simply, if there are no dependent sources present in the circuit, then all you do is you remove or you reduce all independent sources to zero and you find Req, right? Now, if you can't, there are some circuits where we cannot reduce it to a single resistance. Then we would have to do the other way where you connect voltage source at the output terminals and find the current, apply Ohm's law. So how many of you are concerned about your grades? Yeah, take that into consideration. Well, this circuit is not on the internet unless somebody posted it on there because I designed it. So translating the question, okay. Hold on. Hold on. I can't listen. Can you please repeat? With this? Well, this is the end result, though. This is the end result, right? Oh. Maybe my phrasing needs to be better then. Communication needs to be better. Just the first step, yes. Okay, okay. All right. Yes. Yeah, this all it shows up on Canvas, I thought. It's already. Oh, the homework. Okay, okay, wait. Let me. The question being asked is about homework submission scans, not the connect one, right? So the connect deadlines are the ones that students should pay attention. The scanned submissions, I'm gonna go in there and change those, but they are not hard and fast. As long as the work gets submitted for the homework scan submissions, students will receive full credit. I understand your confusion, so I'll change those dates. And thanks for letting me know. Um, that's the due dates you're referring to, right? The homework scan submissions. Okay. So like post an announcement letting students know that it's okay. I'll do that. Absolutely. Our hand was raised here. So I used to do that. And basically had no due dates on them. So suggestion is like have no due dates on them. What happens with assignments that don't have a due date? They show up at the very end of the list, at the bottom of the page. So several students like forget the first day of class and they were like, I didn't submit a single one until the end of the quarter. So if that's what I can do in that case is I can just have them due at the end of every week or something like that. And then again, as I said, the due dates are not that hard and fast for the scan homework. So what I'll do is I'll just change them to a bunch like every 2 weeks or something. So the students have a reminder that they have to submit that, but it doesn't like mess up with the rest of the course. Yes.
Is there any reason why the scan are the same due date as when we submit the homework? Even like if we submit it after.
Because every time there is, yeah, every time there is that I have to go in and manually change every single thing, which seems like a small thing, but yeah, I'll go ahead and do that to have them synchronized. So either have them synchronized with the Connect homework or have them due at least every 2 weeks. Synchronized would be nice. I agree. No, I just need a TA to help me with that. No, I'll keep that in mind and I'll do that. So far we have had homework 1, homework 2. Homework 3 will be coming up. Well, I think most of the time here, but I'll have a, let's see, today's Monday, Tuesday, Wednesday, maybe, maybe I'll make it due Thursday. Okay, I'll post it in advance. I'll cover some material today, and then we'll cover the rest of the material on Wednesday. It'll be a short homework due on Thursday, and I'll post the homework sometime today. Okay. All right. Chapter 2, solid state electronics. Okay. So this is where we learn most of the fundamentals about solid state materials, electronic materials. So most materials that we deal with in everyday life, every material that we deal in everyday life has material properties that are dependent on a lot of on their physical environment. We have temperature, pressure, humidity, moisture. Well, it's the same thing, but primarily temperature and pressure. Okay. Depending on our application, electronically speaking, we have 3 broad classifications, right? We use conductors, insulators, and semiconductors. So again, depending on our application, we might choose a material that is a conductor. Then we might need insulators. And then, of course, the foundation of all electronic devices that we use today, semiconductor materials. The point being that all material properties are dependent on their environment. The one that we focus on for our course and for electronic devices is resistivity. Resistivity. Resistivity is a material property of every element, and it is highly temperature dependent. So material properties in general are dependent on temperature, pressure, humidity, etc. But the one that we are interested in is highly dependent on temperature. Resistivity is noted by the Greek letter rho, lowercase, and units of ohm centimeter. It's ohm times centimeter, okay? It's not ohm per centimeter. Assume you would have learned about this in physics, perhaps, maybe. Resistance R uses the resistivity and it's given by this equation. R is rho L over A, rho times L over A, length divided by the cross-sectional area of a piece of material. So for instance, let's say you have a piece of material. This is the cross-sectional area, and this is the length. And the resistance as measured from end to end would be given by the material property rho L over A. Okay, and of course, units for resistance is ohm. So I want to emphasize the fact that everything that you learn about electronics is highly temperature dependent. So anytime we refer to something, let's say this has a value of, rho has a value of some value, some numbers, it's always referring to as around room temperature, around 25 to 27 degrees C. Okay, that's what we generally accepted convention. So unless explicitly specified, everything is at room temperature. Okay. And based on the resistivity, we broadly classify three types of materials: conductors, semiconductors, and insulators. Conductors have rho typically less than 10 raised to minus 3. Insulators somewhere greater than 10 raised to 5. And semiconductors are somewhere in the middle. They can act as conductors or they can act as insulators. And so it's between broad classification. Insulators or conductors. So they can act as insulators or conductors. All right, 10-second pause. Let me know if you have any questions. Yes. Higher in operating temperatures would require, well, let me put it this way. Anytime energy is transferred, which is what we are doing, electrical energy is always constantly being transferred, heat is generated. When it gets hot, material gets degraded. So the resistivity for conductors actually increases with heat. For semiconductors, it actually decreases with heat. And so that changes your operation of your circuit, especially when we are talking about micro devices, small scale, temperature affects it a lot. So here is the center of the periodic table, column 3 to column 5, where we have the most common semiconductor materials. The most common by far is right here, silicon and germanium. Germanium was actually the first semiconductor material, but silicon quickly overtook it because of the ease. Well, not ease. Well, first is the abundance, right? Silicon is the second most abundant element on this earth, on this planet. And then lots of research went into creating a single crystal material that could be of very high purity. Okay, so when you're creating semiconductor devices, we want our starting material to be as pure as possible. And so there needed to be a way to create a single crystal material of very high purity. And so when they determined a convenient method to do so, silicon quickly overtook germanium. That and for many other reasons also. But we'll cover that beginning here from next class onwards. We are out of time. And so we'll stop here for today and pick it up again next week. Good discussion today. But it took up a lot of time. So yeah,